Welcome to another deep dive. Today, we're going deep into theoretical physics, the quest to find a theory that explains everything in the universe. It's a big topic. So we'll be taking cues from this article that dives into string theory, an idea that's been held up as a potential answer for decades. But we're going to go a little deeper look at why some physicists are starting to question it.
Yeah, it's a fascinating area of physics because it speaks to this, you know, deep human desire to find a simple explanation for the incredible complexity of the universe.
Absolutely. So let's start with Einstein. I feel like any conversation about unifying the universe has to start with him, right?
Yeah, he's definitely the starting point for this whole idea after coming up with his theory of general relativity,
Right.
which revolutionized our understanding of gravity. Einstein spent the rest of his career trying to merge it with electromagnetism.
I can see why he'd be obsessed with that. If you're Einstein and you figure out gravity, it's got to make you wonder if it's connected to this other fundamental force that everyone's studying at the time.
Exactly. But then things got even more complex when two more forces were discovered, the strong and weak nuclear forces. Suddenly, instead of two forces, physicists had four to contend with.
Okay. So that brings us to the Standard Model, which I know is considered the most successful theory we have in physics.
Yeah.
It explains how most of the universe works, right?
That's right. The Standard Model describes three of the four fundamental forces: electromagnetism, the weak source, and the strong force. And it has been incredibly successful at predicting the outcomes of experiments.
Ah, there's always a but in physics, isn't there?
Right, and the big but with the Standard Model is that it can't incorporate gravity. It simply doesn't fit. And this gap, this inability to explain gravity in the same framework, has led physicists on a search for a new theory, one that can unify all four forces.
And that's where string theory enters the picture.
It's exactly. String theory came onto the scene as a potential solution to this problem. Instead of point-like particles, it proposes that everything is made up of tiny vibrating strings. These strings vibrating at different frequencies give rise to all the forces and particles we see in the universe.
I have to admit, it sounds incredibly elegant. But our article points out that it's been around for over 40 years, and we're still waiting for it to deliver on its promise. I'm curious, what are some of the specific issues that physicists are raising?
One of the most significant challenges with string theory is the concept of emergent spacetime. You see, in traditional physics, spacetime is the background on which everything happens. But in string theory, spacetime itself emerges from the interactions of those tiny vibrating strings.
I think that's where I get lost. It's not easy to visualize how space and time, things we think of as fundamental, could actually emerge from something else.
It's definitely a mind-bending concept. Imagine a school of fish. From a distance, the school looks like a single entity moving and changing shape. But zoom in, and you see it's actually made up of countless individual fish interacting with each other. In string theory, space-time is like the school of fish emerging from the intricate dance of those tiny strings.
So the very fabric of reality, the stage on which the cosmic drama unfolds, is actually a consequence of something even more fundamental. That's a huge shift in perspective.
It is. And then there's the issue of extra dimensions. String theory, at least the most widely accepted version, requires the existence of 10 dimensions 6, more than the 4 we experience every day.
Okay, now that's where my brain starts to melt a little. I get the 3 spatial dimensions, and I can even wrap my head around time as a 4th dimension. But 6 more, where are they?
The idea is that these extra 6 dimensions are curled up into incredibly small, complex shapes called Calabi-Yau manifolds.
Calabi-Yau manifold. So these extra dimensions are like tiny, intricate sculptures scattered throughout the universe. I'm trying to picture it, but I think I need a better analogy.
Think of it like this. Imagine a garden hose stretched out across your yard. From a distance, it looks like a one-dimensional line. But if you zoom in close, you see that it actually has a two-dimensional surface that's kind of like these extra dimensions. They're curled up so tightly that we can't perceive them directly.
Okay, that makes a bit more sense. But wouldn't we have detected these extra dimensions if they exist? I mean, physicists are pretty good at finding tiny things right.
You'd think so. But despite decades of searching, there's been no experimental evidence to support the existence of these extra dimensions. And that's a major point of contention for string theory's critics.
So here we have this incredibly elegant theory that seems to explain everything, but it relies on extra dimensions that we haven't been able to find. That seems like a pretty big problem.
It definitely raises questions, and it highlights a fascinating difference in how mathematicians and physicists approach the world. Mathematicians can explore a 10-dimensional space just as easily as a 4-dimensional one. They're not bound by the constraints of physical reality.
But physicists are right. We're stuck in this 4-dimensional world, at least for now.
Right. And that's one of the main criticisms of string theory. While it's mathematically beautiful, it hasn't made any predictions about our four-dimensional universe that we can actually test.
So it's a clash between theoretical elegance and experimental verification. String theory is this amazing mathematical structure, but we don't know if it describes the universe we actually live in.
That's a great way to put it, and it leads to some interesting questions about the nature of science itself. If a theory can't be tested, can it be considered truly scientific?
That's a deep question. It's like we've stumbled upon a beautiful map, but we don't know if it leads to a real treasure or just a mirage.
And that's what makes this area of physics so exciting. It's a frontier of knowledge, where we're grappling with fundamental questions about the nature of reality. But before we get too philosophical, there's more to unpack in this deep dive.
Welcome back to our deep dive into the search for a theory that explains everything. We're picking up where we left off, still grappling with string theory, its potential, and its critics.
As we were discussing in the previous part, string theory offers this beautiful and elegant framework for understanding the universe. But it comes with some significant challenges.
Like those extra dimensions we talked about, 6 extra dimensions curled up into these tiny, intricate shapes. It's a mind-boggling concept, to say the least. And I have to admit, I'm still struggling to fully grasp it.
It's not an easy concept to visualize, especially since we don't experience these extra dimensions in our everyday lives. And to make it even more complex, string theory doesn't tell us exactly how these dimensions are curled up. Each possible configuration leads to a different version of the theory.
So it's like having a massive cosmic puzzle with infinite possible solutions, and we're trying to find the one that fits our reality.
That's a great analogy, and it's one of the main criticisms of string theory. Without any experimental guidance, it becomes a game of mathematical exploration with countless possible universes, but no clear way to determine which one is correct.
It seems like a lot of physicists are okay with that level of ambiguity in the math, but others are less comfortable with it.
That's right. There's a fascinating tension between those who are drawn to the mathematical elegance of string theory, even without direct experimental confirmation, and those who believe a scientific theory needs to be testable.
Okay, but let's step back for a second. We're talking about string theory because it promises to unify the 4 fundamental forces of the universe.
Sure.
Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Can you remind us why that unification is so important?
It gets to the heart of what physics is all about, the search for a deeper understanding of how the universe works at its most fundamental level. We have these 4 forces that seem to operate independently, and yet intuitively there's a sense that they must be connected somehow.
It feels like there should be one set of rules governing everything, right?
Exactly. And that's what a unified theory aims to do, provide a single framework that explains all 4 forces as different aspects of the same underlying principle.
I remember you said the standard model does a great job explaining 3 of the 4 forces, but it's that 4th one, gravity, that's causing all the trouble.
Right. And that's where string theory attempts to bridge the gap. Remember, string theory says that everything in the universe, including the particles that carry forces, are made up of these tiny vibrating strings. And one of the vibrational patterns of these strings corresponds to the graviton.
Wait, the graviton, isn't that the theoretical particle that's supposed to carry the force of gravity?
You got it. It's like the photon, which carries the electromagnetic force, but for gravity. And in string theory, the graviton emerges naturally from the vibrations of the strings, just like all the other particles. It's a beautiful and elegant solution to the problem of incorporating gravity into a quantum framework.
So instead of having different particles for each force, string theory suggests that everything, including gravity, arises from these tiny strings vibrating in different ways. It's like a cosmic symphony with each note representing a different force or particle. It does have a kind of poetry to it.
It's a very compelling picture of the universe. And that's one of the reasons why string theory has captivated the imaginations of so many physicists. It offers this unified view where everything is interconnected and emerges from a single fundamental entity.
But then we're back to that question of testability. If we can't experimentally verify the existence of those extra dimensions or those tiny strings, how can we be sure that string theory is more than just a beautiful mathematical construct?
That's the central debate in the field. Some argue that the mathematical consistency and elegance of string theory are strong enough to warrant continued investigation, even without direct experimental evidence. They believe that as our experimental techniques advance, we'll find ways to test its predictions.
But there must be a lot of physicists who aren't convinced, right? I mean, it seems like a pretty big leap of faith to accept a theory without any empirical support.
You're right, there are many physicists who are skeptical, and their argument is, well, why focus so much energy on this one theory that seems impossible to test? There are other approaches to quantum gravity that might be more grounded in empirical observations.
So there's a real tension between the theoretical beauty of string theory and the need for experimental verification.
Exactly. And it's an ongoing debate within the physics community, but I think that's part of what makes this field so exciting. We're dealing with questions that are fundamentally about the nature of reality, and there's no easy answer. It's a journey of exploration, of pushing the boundaries of knowledge, and it's still unfolding.
Welcome back to the final part of our deep dive, where we've been trying to wrap our heads around string theory and the search for a unified theory of the universe. It's been a wild ride, to say the least.
It certainly has. We've covered a lot of ground, from the elegance of string theory's core idea to those head-scratching extra dimensions and the ongoing debate about its testability.
It's almost like we've been on a quest for a hidden treasure, this theory of everything, following a map that leads us to some incredible vistas, but also leaves us questioning if we're on the right track.
That's a great way to put it. And I
Yeah.
think that sense of being on a journey, a quest for knowledge, is what drives a lot of physicists,
Mm.
especially those working in theoretical physics.
So where do we go from here? What's the future of string theory? Is it fading away, or are physicists still holding on to hope that it might be the answer to unifying the universe?
Well, it's hard to predict the future of any scientific theory. The landscape of theoretical physics is constantly evolving, and what's in vogue today might be out of favor tomorrow. But even though the initial excitement around string theory has cooled down a bit, it's certainly not disappearing.
So it's not game over yet.
Not at all.
No.
There are still many talented physicists actively working on string theory, exploring new approaches, refining the mathematics, and looking for ways to connect it to observable phenomena.
Yeah.
It's a testament to the power of a really compelling idea. It can stay with you, even when the evidence is elusive.
That's interesting. So even if string theory doesn't end up being the ultimate answer, it sounds like it's been a valuable pursuit.
Absolutely. One of the things I find most remarkable about string theory is how it has pushed the boundaries of theoretical physics, forcing us to think in entirely new ways about space-time and the fundamental nature of reality. It's like it opened up a whole new dimension of thinking, even if those extra dimensions haven't shown up in experiments.
I like that, opening up new dimensions of thinking, if not literal dimensions. And you mentioned earlier that even if string theory doesn't directly solve the unification problem, it still led to some important insights in other areas of physics.
Right. We talked about how studying lower dimensional models inspired by string theory helped explain quark confinement in quantum chromodynamics. That's a really significant contribution, and it demonstrates that even if the theory isn't entirely correct, it can still spark valuable discoveries in unexpected places.
So it's like a ripple effect. String theory throws a stone into the pond of physics, and the ripples spread out, creating new waves of research and understanding.
That's a beautiful way to think about it. And ultimately, that's what science is all about, pushing the boundaries of knowledge, exploring new ideas, and following those ripples wherever they may lead.
So to our listeners, we've reached the end of our deep dive into string theory and the search for a unified theory of the universe. What started as a quest for a single, elegant equation to explain everything turned into a much richer exploration. We've encountered beauty, controversy, and moments of both frustration and awe.
And even though we didn't emerge with all the answers, I hope you've gained a deeper appreciation for the incredible ambition, creativity, and sheer intellectual firepower that physicists are bringing to bear on some of the biggest questions humanity has ever asked.
It's a reminder that science isn't just about finding the right answers, it's about asking the right questions. Being willing to embrace uncertainty and continuously refining our understanding of the world around us.
And who knows, maybe the next Einstein, or perhaps a whole team of brilliant minds, is already out there on the verge of a breakthrough. That will revolutionize our understanding of the universe.
That's what makes it so exciting. The future of physics is full of possibilities, and the search for a unified theory continues.
So the next time you look up at the night sky, remember that those twinkling stars and distant galaxies hold mysteries that are still waiting to be unraveled. And perhaps, just perhaps, hidden within those mysteries are the clues to unlocking the universe's grand design.
Thanks for joining us on this deep dive. Until next time, keep those brains buzzing. And never stop questioning the universe.